My name is Eduardo, and I'm going to tell you about dynamic complexity of laser-induced self-organization. So this is work that I'd like to thank the organizers for this opportunity to. And here, this is work that started long ago during my PhD thesis, in which I became interested in this topic of complexity. So complexity is a bit everywhere around us. It's spotted in the clouds of Jupiter, in the way that birds flocks in the sky, in the way that the cosmic microwave background is not in the way that cells organize, in the way that crystals organize, in the way that patterns form on the coats of leopards and jaguars. It can also be spotted on, we can also find a meaningful notion of complexity in the models that we use to study these complex cells, such as machine learning models. So this is very easy to spot, very easy to recognize, but quite difficult to define. Because the definition that suits different topics might be very different, and might focus on different aspects of reality. So we can also spot complexity in those tiny patterns that you see over there, which are formed by femtosecond laser radiation on the surface of nickel. And they're created over here, just across the street, just across the courtyard, at the Hubert Lab. So these patterns were the topic of interest of my colleagues Anthony Lapoule and Jean-Philippe and others, who were interested in these patterns, and specifically in the way they form. So one key question was understanding the nature of the process that led to its formation. So is it hydrodynamic in nature, or is it electrodynamic in nature? So this was the key question that we're interested in solving at the time. So to answer this question, I worked together with my colleagues. We worked on a physics-informed machine learning model in which we combined physical information in the form of a partial differential equation that is hydrodynamic in nature, with very few data, to build a machine learning model that was able to accurately predict patterns in regions of parameter space, laser parameter space, that were not determined. So what does this mean? We have hydrodynamical information, we have few data, and we're able to successfully train a model to predict things that we didn't observe before. So this means that this strengthens the cause for the hydrodynamic nature of the process that leads to the issue. So this was a big deal at the time. And I'll spare you the details of the construction of this model, but I will go into, but I will say that it is the variety and the regularity at the same time of the patterns that allowed us to do this successfully with only few data. So what do I mean by variety and regularity? So over there you see, so you can think about these surfaces as originating from fairly homogeneous initial conditions. So you have a process, you have a surface that is treated quite homogeneously, and at every point you're going to have roughly the same simplish process that will evolve and make the surface evolve. Okay? So if the process is simple, it can still create a variety of solutions if it's able to amplify the noise in these initial conditions. But at the same time, there has to be some sort of long-range interaction between these solutions so that the variety is reeled in. So you have some sort of regularity that comes from an interaction range that is long. Okay, this is what I try to represent here, not very successfully. Okay, so this notion, this combination of variety and regularity will be familiar to you scientists, because as scientists, we try to make sense of the world by looking into different aspects, which I can call these decompositions over here into components C1, C2, C3, etc. So what we're looking for is decompositions or aspects that are sufficiently diverse so that they may merit our interest, but also sufficiently connected so that we might spend a long time looking at these very interesting connections between things. So this is what I will call complexity, this combination of diverseness and connectedness. If this complexity is large enough, this might even merit a scientific field like physics, which is hundreds of years, and machine learning, which is quite recent, but so this still leaves diversity and connectedness to define. And if Occam's razor serves us, the easiest way, the most straightforward way to combine two quantities that have no reason to have the same magnitude and that both into a quantity that increases in both two is by multiplying them together. So we're going to make this hypothesis. We're going to define complexity as a product of diversity and connectedness. And we're also going to look for complexities that depend on distribution. So we don't look for the complexity of the thing. We're going to be interested in the complexity of the distribution of the things within. Okay? So this will allow us to apply this measure to different things, to different objects. Which will be interesting. Once we do that, we almost directly have Shannon entropy there as a measure of diversity. So this is the standard measure of diversity. There's others, of course, but this is a standard measure of diversity in the following sense. So if you sample from this distribution, Shannon entropy will measure the expectation of your surprise in these samples. So as measured by minus log p. Still leaves the matter of defining connectedness, which I seriously write as D. So we still have something to define. So before I proceed, I'd like to give you a fake insight. So one might be tempted to think that connectedness and diversity usually are usually in opposition. So you have something that is very diverse. Usually this means that you can't really establish that many connections. So this is often the case. It's not always the case. So this motivates the following definition of connectedness D. So you might have a decreasing function of diversity, and replacing that connectedness with this decreasing function, you find yourself a curve for complexity as a function of diversity, or entropy in this case, that looks like that. This really looks good. It has the correct shape. So if you look at the left over there, you will find something that is not diverse enough to merit complexity. And if you go to the right over there, you have something that is so regular, so undiverse, if you will, that is not does not merit the name complexity either. So this is all good. So we have something that has the correct shape, but the choice of this measure of connectedness was quite arbitrary. So if we replace it with other measures of connectedness, we will find the maximum at different locations. And this is really a huge problem in this case, because this destroys the semantic meaning of this complexity. So what we say that is maximally complex will change depending on this definition of time. Okay, so this is a big problem. This, unfortunately, is the problem with what is the de facto standard definition of complexity that involves a product of H and D. And this is where I solve the mystery of calling D connectedness D, because the authors, Lopez Ruiz, Mancini, and Calvet, who came up with this measure of complexity that they call the statistical measure of complexity. Statistical because it's distribution in nature. They call D over there the disequilibrium. So, and I'm trying to keep to that notation. So they define disequilibrium as sort of like what we had before. So a distance or a difference between H max and H, but there's the higher order terms in an expansion, terms of order 3 and higher in an expansion, in a Taylor expansion around the Mach center distribution of H. So the good thing about this measure of complexity is that it has the correct shape necessarily. So you have something that does exactly the same as the other one, although the shape will change a little bit. It is standard, and it is standard with good reason because it has many applications. It has been applied to image segmentation tasks, to analyzing molecular dynamics, etc. And importantly also, it is non-trivial. So the measure that I had before is arguably not a function of the distribution, but a function of entropy. It's the only way that it depends on the distribution is via the entropy. So this is no longer the case for this definition of connectedness, in which we have we destroy this dependence on the entropy. What is not so good is that we did not destroy the arbitrariness in the definition of connectedness. So we have something that is just, we came up with a measure. The measure works, but we came up with it, that there's no other argument. Our physicist friends are slightly concerned that this quantity does not transform correctly. So when you change coordinates, you don't transform as it should. And most importantly for us, there's no direct connection to physics. So if you apply diversity, so if you measure diversity using Shannon entropy, and the object or distribution, the physical distribution, you make sense of it, you know what it means. But this H max minus H plus some higher order terms. So to address these issues, I'm going to propose a measure of connectedness that tries to make sense which tries to give a notion of system size in a distribution way. So I will do that using something called Salus entropy. And details aside, this is a measure of diversity in roughly the same sense as Shannon entropy. So it is sort of an expected surprise, where surprise is different, is defined differently, but it's also an expectation of surprise. Importantly, there's a free parameter over there, which is Q, the entropic index. And also importantly, this measure is non-additive. So what this means is that, so for Shannon entropy, if you have two random variables that are independent, and if you want to compute the entropy of the joint distribution, you just add up the entropy of the margins. Okay, so this is no longer the case for Salus entropy. You have this multiplicative effect that is modulated by the entropic index over there. So this entropic index measures or determines the degree of non-additivity in this way to combine things. So what does this have to do with system size? In physics, physicists are interested in the distributions, but they're mostly interested in things, in physical things. And physical things usually have an extension. You have a natural notion of size, a natural notion of size, of extension, and you want to see how your measures behave with respect to changes in this extension. Okay? So we call a quantity extensive if it scales proportional to the system size, which we define in terms of number of particles, for example. So this is why entropy is considered to be extensive, which is a sentence that is only partly true. So entropy, in the sense of Boltzmann-Gibbs entropy, is extensive. So it scales linearly with system size if the parts within that system do not interact. If they do interact, so if you have interacting parts, this measure is no longer extensive. So the same thing could be said about Salis entropy. Salis entropy, for Salis entropy, there's also systems for which it is extensive and systems for which it is not extensive. But crucially now, we, unlike for Shannon entropy, we could ask the following question. So instead of wondering whether this system, so whether entropy is extensive for this system, we could, given a system, try to find the entropic index Q that will make the measure extensive. So this measure becomes special because this measure is sensitive to the way that the system size scales with entropy. So this is my proposition. Because there's no other standard method to determine the right entropic index, I'm going to choose the entropic index that this is a special entropic index that will make the system extensive with respect to this measure of entropy. And this is found, so if you expand that a little bit, you end up with this equation here at the bottom. If you solve this equation for Q, you end up with a Q, an entropic index that reflects how the number of accessible states scales with system size as measured in entropy. Okay, so this is a special Q. Now we have a notion of connectedness, we have a notion of diversity that we chose, and we need to apply it to something. So we are interested in dynamics, and the standard measure of, for the standard way, not the standard, but the simplest way to estimate time series dynamical diversity is via permutation. So what we're trying to assess is how diverse the possible trajectories that the system might take when it evolves using that a certain process. So this is hopelessly complicated because it depends on initial conditions, it depends on direction, it depends on how long we wait, it depends on many different things. So in order to simplify this, we're going to squint and we're going to look at the system, not as a series of actual dynamics. We're going to look at it just as ordinal patterns. So the question that we're going to pose is it going to go down and further down, or is it going to go down and up just between the two? Okay, so you have what we call ordinal patterns. We're going to check, we're going to follow the dynamics, we're going to count how many ordinal patterns we find at each of these slots. We're going to compute the entropy using Shannon entropy, and this gives us a measure of diversity of trajectories. Simple to compute, and moreover, it has good theoretical properties because it converges to those more pure measures that follow. Okay? So the problem in extending this to higher dimensions is that, well, the first one is that there's no natural order in higher dimensions. But we can actually address this because if you remember, what we did before was just we squinted a little bit and we tried to represent the dynamics just using shapes, but shapes in 1D. So shapes in 1D can be just, so shapes in 1D correspond roughly to order, okay? Or to signs, if you will. So what we're going to do is we're going to generalize this notion of shapes in a way that is more convenient to use in higher dimensions. So we're going to use the derivative, and we're going to use the sign of the derivative to define a sort of a dictionary of shapes. So this is what it looks like in one dimension, and this is what it looks like in higher dimension, where we just take the sign of the derivatives in different patches. And we encode, so we call each of these patterns by the name that is given by that minus, plus, plus, minus, minus, plus, etc. So it's just a sequence of zeros and ones that identify each of these patterns. So this can be done in arbitrary dimension, and then we can compute the entropy of this sign distribution, this sign pattern distribution, and we get a measure of diversity of dynamics. Okay, that is simple to apply. If you can do it to different images, of course, you have to assume that there's some important sort of publicity involved. But anyway, so this is, regardless, this is a measure of diversity in trajectories. So our dynamical complexity is with H being the Shannon entropy of this sign pattern distribution that I just defined, and Q being the entropic index of the Thales entropy that renders this distribution extensive in the sense that I just defined, is simply the product of H and 1 minus 1. This is very simple to compute. This is cheap to compute. This is interpretable in the sense that I just gave you, and it has a clear connection to the underlying physics. And also, it is applicable to a number of different systems, and it scales from nanometer to the parsec, actually to megaparsecs. So, because of the way it was constructed, it's magical. So this is this is a representation from my colleague Fayad of the evolution of nano patterns when you increase the number of pulses. So you look at those at how the patterns will change as you increase the number of pulses. So you have sort of a discrete dynamics, if you will. So looking at it, you see that the patterns become more regular, more complex, and then this complexity, which is not the same for every single sequence of patterns. And in applying the measure of complexity that I just defined to these patterns, you see you are able to detect to characterize the patterns by their complexity in a way that makes sense. And if you look at this slice of a simulation of the universe by Ian Brazera, where you can see that so Z over there is the redshift, and this is on the scale of 124 megaparsecs divided by the Hubble constant there. So you see that there's structure over there. There's roughly, you see those threads, so this is interesting, it's complex. So one interesting question is when you change the model that generates this dynamics, if the sort of large scale statistic that allows you to distinguish between two different models. So in this case, W cold dark matter and lambda cold dark matter. And indeed, when we applied this measure of connectedness, in this case, in the y-axis over there, and when you apply it to these simulations of the universe, and as you change redshift, so if you go back in time, if you go forward in time, you see that you are able to distinguish between these two models of universe dynamics in random basis. Thank you very much for your presentation. So you have questions and my equations. I just have the point. One would entropy. Sorry, in such a complex case, why would entropy like to? No, it would not be at. Yes, but John, looking at the inequalities. So I'm looking for a measure of diversity. So I'm looking for a measure of an entropy that will look at the system as roughly composed of parts that scale with system size. So this is not an entropy. So this roughly discounts the connectedness between the parts. So I'm looking for a measure that does this. And well, in a perfect gas makes sense. Okay. Such complex skills. So for me, what this means is that you're taking into account the interaction and still getting a measure that is extensive. So you're kind of discounting this the interactions between the parts and still obtaining a measure that is extensive. does not recover. So you get a measure such that if you break the system into parts, you get roughly the same thing as if you had, and you compute the thing, you get that. So you basically are forgetting, are becoming blind to the interaction via the measure. So this is a special point of the measure. So I'm not interested in, this special point of the measure is good because it will discount, it's the point that allows me to discount the interaction. So you see, this is a measure of the interaction strength. This is a very good question. So what I'm looking for is not measuring the complexity of the system. What I'm looking for is a way to measure how much it is connected. So the way that I'm going to measure this connectedness is I'm going to take a measure and I'm going to turn it into something that is extensive by 2 of this parameter q. And I'm going to say that this parameter q that turns it into an extensive measure is special because it's exactly the one that accounts for the interaction strength between all its points. So I take it as the parameter that measures the interaction strength. So see, that's the point. So I'm trying to measure how connected the system is. Okay, so this is, I'm doing it via a measure. Okay. Questions?
This value of Q, does it depend on the size of the system?
For uniform distributions of this kind. Which is, so I don't know the answer for other cases. I think it's a question that's pretty.
I think that's a very naive question. By the way, very naive question. Know that you have this measure, these curves over time.
Yeah.
How is it useful? This portion of the surfaces, and then behind this, how is this relevance or some purpose might have this?
Okay. So for the universe case here, so we have 2 dynamics, and we want to find the statistics that allows us to estimate dynamics. So in a system that is hopeless, okay, so this takes place over a great deal of iterations. It's a really complicated thing. So we are able to characterize the dynamics using X. Exactly. So this would be hopefully useful to do that in the case where we want to model the evolution of these patterns as a dynamic system. So we want to make statements about how this evolves. This is one possibility. Another possibility, so if you want to be a little bit more maybe interesting, so you could look at these things and you could in general, you might want to be looking for aspects in which this notion of complexity is maximized. So these would be maximally interesting points, whatever the configuration space is. So if you want to optimize, so one thing that we can do with physics and machine learning is we can explore the solution space of a certain equation. So we might want to explore the solution space of a certain equation that in a direction that maximizes complexity. So this is defined in this way that I did, which is a way that makes sense. So arguably there's all these things, this construction, but I think like this would be a way to find strictly pattern exploration. That's
I have a question about the this lecture hall. There are students, master students from master programs, both physics and machine learning. So I have a tricky question about the relation of machine learning. So you explained during your talk that complexity is something at crossroad at the interface between diversity and connectedness. Okay, so this is business. On the other hand, in machine learning, we say that the complexity measures in some way the risk for a family of hypotheses to overfit the data. How to relate those two notions? Because what is a bit weird is that you explain that the complexity is the largest when the set organization of pattern, when the patterns is very well organized, right? So this is something we should learn, whatever the expressiveness of the model we would use in machine learning. But on the other hand, in machine learning, the largest the complexity, the higher the risk of overfitting. So there is something which is, you see what I mean?
I think I see.
So I would like to just to probably it corresponds to two different notions, or if not, how do you relate?
Hopefully, this is the direction that I'm going for. Hopefully, it will not correspond to such different notions. So hopefully, the idea here. So I have a partial answer to that. This is still more going for. So, but if you explore what it means for the distribution to maximize this complexity. So if you look for a distribution, so you have a distribution, say, of parameter weights. And if you look for the distribution that maximizes Shannon entropy, you will find something that is this is a standard result. If you look for something that minimizes Shannon entropy, you get something that is concentrated at just one point, so a delta function. And if you maximize this notion of complexity, preliminary results indicate that you get sort of a direct home. So you get something that is in between. So you get something that is multi-home. And this is quite interesting, I'd say, from the point of view of this interpretation. So you're looking for something that is somewhat in between. So either in solution space, configuration space, all these projects, which they're looking at how neural network weights change in dynamics.
I was for the when you show what you got and do you have any scale of the patterns you observe?
Yeah, these are really tiny. So this is so onto sorry, microns plus nanometers plus. Sorry. So it's the scale is not there. Yeah, but they're very small. So here, what this means is that in the sense that I just defined, complexity is going up to the point, and then it's going to increase. So this is for the series one. So as you see over there, so there's a certain average organization kind of like maximum, and then it starts becomes chaotic. So it just for this organization is also. So I can't really advance. So if you look at the connectedness, so what this means is that the interaction range will decrease. So this is basically what's happening. Because the process, I would say the process is as diverse as it was. So it's actually the long range interaction that is. So if you think about radial architecture, this is really so the location of the roles, so where they start, is really to expand depends on the actual location. But there's this notion of interaction. This is not the same as they're not dependent on distributions. What happens inside these roles, but they are roles enough. Regardless, there are roles, and it's the fact that there's a role size that makes the possibility of the ball exist. So that there's this interaction. It's the existence of a long-range interaction that permits.
Thank you very much again.
Thank you, Rado.